Okay, so we want to talk about transformers. So first of all, let's go over and look. So here is a basic transformer. So we basically have a magnetic core material, and we have wrappings on one side and wrappings on the other side that are going to create this flux. So let's grab this picture right here so I don't have to draw it myself. And we will copy that over here. Okay, so the first thing that we're going to do is we're going to look at what is this magnetic circuit. Okay, so we have a winding right here and a winding right here. Well, we found out that the windings with applied sources, those become our magnetomotive force. So let me make my picture a little bigger so that we can kind of see. So what we're going to do is we're going to use our right hand rule, and we're going to take our fingers and wrap them around the direction that the windings are going. So on the left-hand side, we're wrapping around this direction. My thumb is pointing up. So that means that I'm producing a flux going up. So we're going to come over here, and on my primary side, this is going to be equal to N primary times I. Okay, now we're coming over to our other side. And so now you see that the windings are going this direction. So again, on the right-hand side, I'm wrapping my fingers around the direction the current's going. Now my thumb is pointing down. So that's going to produce a flux going down. So that's going to have polarity like that. See if I can draw that a little bit better. So that's going to produce, and this is my N secondary times my I secondary. This was I primary. Okay, so now what we have is now we have this material going around. So that's going to create my reluctance. So I'm going to come up here and I'm going to have a reluctance like that, which is my magnetizing inductance is what they call it, which is going to be equal to the total length of my magnetic core divided by mu times the cross-sectional area of my core. Okay, so now we can make my picture a little smaller so that we can see better. And so now here is my magnetic circuit. So now what we have to do is we're going to be looking at voltages. So I'm going to look at Faraday's law. So Faraday's law of induction says that the EMF, which we call voltage lots of times, is equal to minus the derivative of my flux with respect to time. So I'm going to come over here and I'm going to say that my EMF, which is equivalent to my voltage, is equal to minus the derivative of the flux with respect to time. Okay. Um, so we have to find out what my flux is. So I'm going to go and look at my magnetic circuit right here and solve my magnetic circuit. So I have my flux, which is equal to my N primary, I primary. Well, let me just do this as a full circuit. Let's just do a KVL, which applies just as well here. And so I have minus NPIP plus my reluctance times my flux minus my NSIS equals 0. So I did KVL around this loop. Okay, so we see that my reluctance times my flux is equal to N primary times I primary plus N secondary times I secondary. Okay, now typically if this is a good transformer, we want this to have really high inductance, which is going to have really high uh, reluctance. Okay, so typically we are going to look at Rm equal to 0. So we're looking at our reluctance and setting our reluctance equal to 0. And then we have N primary times I primary plus N secondary times I secondary equals 0, which is my circuit. So now what we can do is now we can come in and we can look at our flux and go back to Faraday's law. Okay, so let's go to Faraday's law. So Faraday's law says the voltage on my primary side is equal to N1 times dV dt, and the voltage on my secondary side is Ns times dV dt. Okay, well, you see that the flux is the same for both of them. So we produce one flux for my whole core. Okay, so then what we have is we have d flux dt is going to be equal to Vp over Np for my primary side, and it's also going to be V secondary over N secondary. Okay, and so what we see right here, this is my transformer equation. Okay, and so then we could use that to do voltages, and then we could do the same thing for the currents because the power doesn't balance. So let's kind of review this again. So we basically were able to use our magnetic circuit to get this to all work out. And this is my ideal transformer. Okay, so now that we did the ideal transformer, now we want to start looking at, well, what if our transformer isn't ideal? So we're going to start with non-zero reluctance because the chance of us having perfect reluctance isn't really high, so you're always going to have some reluctance in it. Okay, so let's go back to look at if I actually had some reluctance. So we had flux times my magnetizing reluctance is equal to N1 N P I P plus N secondary I secondary. Okay, and so what we're trying to do is we're trying to find our flux. So we're going to take our flux, which is equal to NPIP plus NSIS divided by my magnetizing reluctance. Okay, then we're going to Faraday's law. So with Faraday's law, we have Vp is equal to N primary d flux dt. Okay, so then we can plug that into our equation. So our primary voltage is going to be equal to N primary times d dt of, oh, then we have all of these terms up here. That is the voltage on our primary, okay? And so what we're trying to do is convert this into a circuit, into an inductance. So what we're going to have is this is going to be equal to my magnetizing inductance times di magnetizing divided by T. Okay, so what we see when we do all of this is that my Lm is going to be equal to Np squared divided by my reluctance. And my magnetizing current is equal to I1 plus N secondary over N primary times my I2. So let's draw what this is going to look like. So we have some magnetizing inductance, which has a value of Im, and it has a current going through it of Im, which is equal to the I1 plus Ns over Np times I P. Okay, and then we're going to combine that with my ideal transformer, which has NP to NS, and you see that this piece right here is my I primary, this current right here is my I secondary, then you see I have my V primary here, and I have my V secondary there. So If I have non-ideal reluctance, I end up getting some inductance that's in parallel with this. And so I want this inductance to be as large as possible. Okay? Okay, so now we want to look at our next non-ideality, and this is called leakage inductance. So let's go find a picture. So here is a picture right here that talks about this leakage inductance. So the goal is that this magnetic material kind of holds all of the magnetic field inside. So if I create things right here, my flux is going to stay contained inside of this. Well, the electrical conductivity of a typical metal is way higher than the permeability. And so we don't hold all of the magnetic field lines inside this material. So you see I get these couplings over here, and you see I'm going to get these magnetic field lines that go outside. I might get some that kind of couple all the way back around, and you're going to get the same thing over on this side. So these are called leakage paths, and they create a leakage inductance. Okay, so if I want to model my leakage inductance, I am going to come in here and I'm going to add in a inductance in series. Okay, and I'm also going to have one over here. Okay, and so these are going to be labeled like L of my secondary leakage inductance, L of my primary leakage inductance. So what you see is that I'm going to have my big inductor in here, and I'm going to have a series inductance along here. This one's in parallel, so I want my magnetizing inductance to be really large, and I want these inductances to be really small, okay? So now the next thing that we have to do is we have to look at resistive losses, okay? So we basically have, if I go up to my picture right here, we have a winding right here and a winding right there. Well, these are real wires, so they're going to have some series resistance, okay? So I'm going to come in here and I'm going to add on a series resistor over here and a series resistor over here. And those are going to be the resistance. And so we're going to call this our primary, and this are secondary. And these resistances are caused by the resistance of the wire windings. Okay, so the next thing that I have is I have what's called eddy current loss and hysteresis loss. Okay, so let's look at these two losses. So let's start with eddy current. So if I look at this picture right here, if I have a magnetic field that's moving over a conductor, I get these little induced electric flows in the material. Well, those electric flow in the material, well, these plates, this is electric flow inside of my magnetic material. So if I go back to this picture right here, what's going to happen is I'm going to get some electric fields that are going to flow inside this magnetic core, and that's going to create heat. Okay, and so that's called eddy current loss. Okay, and then I have hysteresis loss. And so hysteresis is when this is moving as my inductor, okay, then my magnetic field's going up and down and up and down. And so it's basically because of the hysteresis, it's going up a different path that it's coming down. And this movement in this area is going to create loss. And so the skinnier this is, the less hysteresis I have in my material, then I'm going to end up getting less loss. And so that's called a soft magnetic material rather than a hard magnetic material to reduce the hysteresis loss. And that's just going to produce heat as well. So how do I model these two effects? Well, I'm going to come in here and I am going to put a resistor, and that's going to be called a core resistance. Okay, so let's redraw now our transformer model. So I'm going to have a resistor and an inductor, and then I'm going to have a core resistance and a core inductance. I'm going to have my ideal transformer. And then over on this side, I'm going to also have my leakage inductance, my winding resistance loss. You see, I put all of my core loss over on one side, okay? So this is going to be labeled R core. This is R primary. This is L primary. This is called my magnetizing inductance. This is L secondary and R secondary. And this is my ideal transformer right here, okay? And this is the model of my transformer. That's a much more accurate model of a transformer. And sometimes we are going to neglect certain terms. Sometimes we'll add them in. Sometimes we'll just do my ideal transformer. But this is what happens when I add in those other losses.